So let's go. Again, it's nice talking to a very technical audience. My background is in computer graphics. Computer graphics is what's behind our ability to do all of this. And then there's a lot of good computer science behind that computer graphics, which is behind the scientific visualization. So I hope you don't mind if I indulge a little bit. But again, this goes to helping you to understand how to master this tool, to really understand what's going on, as opposed to, again, any type of GUI, you can start doing things, you get some results, maybe some unintended results. But again, I think all of you are here this week because you really want to understand what's going on in HPC, what's going on in your visualization. For fun, in that geeky sort of way, our friends from Pixar, Toy Story, Bugs Life, all those good things, Finding Nemo. They make a product called RenderMan. And they, in 1990, which is really scary because most of you weren't born then, they made a sequence of images called the Shutterbug sequence. That's great. It takes a simple scene and runs it through a variety of stages, from getting modeled to getting it on the screen to adding additional levels of realism. I'll leave it for you all to look at, but things like the accuracy of the modeling, the accuracy of the lighting, and so on and so forth. This leads us to OpenGL, which is behind most graphics even today. Actually, you can see they stopped updating OpenGL in 2017. People thought it would die. It's still alive and kicking. It's not being expanded, but it's still out there. It is being replaced, like Apple no longer uses OpenGL. They have their own thing, I think it's called, so on. But a lot of Linux systems still use OpenGL in a software implementation called Mesa. The thing that's interesting about this is there are approximations to what really happens in the real world. So it's a collection of approximations. In a minute, we'll talk about something called ray tracing, and the reason people are excited about that is suddenly it gets us away from a world that is a collection of approximations, and it lets us in a more uniform way simulate how light interacts with things in the world. Okay. So there's all kinds of things. We could spend an entire week just talking about the math behind 3D graphics. But in a nutshell, we're using a right-handed coordinate system, Cartesian coordinate system. Right-handed meaning that you wrap your fingers from the x-axis to the right axis. The right thumb will point towards the positive z-axis. Is it possible to have a left-handed coordinate system? You bet. Okay? But we're using a right-handed coordinate system. It's also, by default, y up, z out of the screen towards you. As you probably know, transformations are order dependent. You pick this up somewhere along the way in geometry class or something, but it's definitely the case here. A little bit of fun. There's some really lovely mathematics behind computer graphics. One of the things is the use of homogeneous coordinates that makes things like projections from a non-parallel space possible. What if you have different coordinate systems? You're doing some, your simulation, you're doing some geo-coordinates, which would be some type of spherical coordinates. Of course, you can just convert those into Cartesian coordinates. And we mentioned that the transformations are order dependent. Okay, models are polygons are what drives most computer graphics up until recently. Again, game engines are now getting into ray tracing, but for the past 30 plus years, it's been polygonal modeling, and that's still what sort of rules the roost and determines a lot of things. For viz-specific types of modeling, we've already talked about having these computational grids and volumes, and of course, we can do things like point clouds and such. So you'll see, even in ParaView, if we want to make a sphere, it's going to give us a lousy looking sphere unless we go in and actually change the number of polygons that ParaView is using to approximate that sphere. And it is possible to put things together in hierarchical modeling. For example, if we had a car, we might want the wheel might be made up of a tire and a rim and such, and so as those turn, we want them to turn together so we can create hierarchies of transformations. Okay. When we get into lighting, it turns out there's multiple different types of light. Again, approximations. There is no ambient light in the world, but again, OpenGL, they found pretty quickly, hey, if we don't put something in there, everything's really dark, okay, or the lighting is very contrast. So they give, 10% of light to everything. And that's what they call ambient light in OpenGL. In the real world, directional light, our friend the sun, pretty much rays come in more or less parallel. Lights in this room would be what we would call point lights or spotlights. So again, we have those same sorts of simulations in computer graphics. ParaView exposes something like that. Materials, it's cool. Anyone know what the difference between like a metallic material and something that looks plastic? Interesting bit of physics I learned in graduate school. Turns out that things look plastic because they have a white highlight. So if you look at that little table there, it turns out the ones that look plastic have a white highlight, whereas those, say further to the left, which have more of a color of the base, look more metallic. And so that's the nature of the difference between plastic. It has to do with how color pigments are suspended in plastic polymers. How we apply light to a surface, we can do these calculations, and you can see if we do more complicated calculations, we get more accurate looking things. So this goes into interpolation. How we control the viewpoint. What you'll actually see is sometimes you're moving through a visualization and stuff starts falling off the back, or gets what we call clipped because there's finite precision in the depth buffer, so that we can only, that keeps us from rendering things that are too far away, that project very small, or that are too close to our faces that would obscure things. Okay. And finally, there's things, we'll see our friend, the depth buffer is how we actually get things to occlude other things. And again, these things are exposed, for the most part, in ParaView. Sometimes you have to go looking for them, but it is nice. There's sort of a nice parallelism to there. Camera controls is one of those things. My second best tip. First tip, remember, look at the information. What type of data do you have? Second tip is control the cameras because it is possible. You click in the 3D window if you play with ParaView. Sometimes it does what you think it's going to do. Sometimes, like that head actually comes in at a weird orientation, and things can be difficult. So use these views, these buttons there to set to those canonical views, to roll the camera, to zoom to all the data there. So there's a number of things there. And ParaView does let us actually create multiple windows in the upper right corner. It lets us split the views, and we can actually link the cameras between those views. A couple of other things about computer graphics. There are some things that are particularly important for scientific visualization. One technique we can do is make surfaces transparent. That turns out to add a lot of work to the rendering pipeline. And again, if you think about it, it's important that the transparent objects get rendered in the proper order. So there's a whole thing about depth peeling to get the rendering more correct, like we have in the lower right, as opposed to the incorrect rendering in the upper right. Texture mapping, we saw the head work very nicely. As long as we have a uniform image set, we can actually slice through, or actually the graphics hardware will slice through it, and we get this beautiful rendering, regardless of the direction that we view it from. Suddenly you mess that up, and suddenly that's not a regular grid anymore, and then it has to go to a different type of rendering, a tetrahedral volume rendering, and suddenly things slow down quite a bit. So I like this, that there's logical reasons why things are fast and slow. We already talked about ISO contours, and there's marching squares that gets those, and it's called marching cubes in 3D. Last thing I'll say about rendering is ray tracing, because this is now built into ParaView. And again, this is a way of, rather than taking the polygons and projecting them on the screen, it actually works the opposite. Light in the real world travels from light sources, hits surfaces, and then some of it makes it to our eye. So ray tracing is running that in reverse. The rays are coming from our eyes through the scene and seeing what it hits, and hopefully then eventually bouncing around the scene till they hit a light source. Or if they don't, then they're completely in shadow. So again, shadows is one of the things that we can see that ray tracing gives us. Also more realistic materials, reflections, and so forth. Okay. What's the value in visualization? Well, you can see the top image here on the left, maybe some type of molecular simulation without shadows and with accurate shadows. You get a really great sense of depth. And those are just static images. Again, if we have streamlines, again, a lot of that pops out. And if we're trying to do some product pre-visualization, again, you can see the value of having realistic materials, lighting, and shading. Ooh, that looks terrible. Ray tracing also gives us different lens models, soft focus. You can see depth of field in that. And there's lots of renderers out there. One thing we'll see in ParaView is they have something called a path tracer, because when we're sending these rays around, if you only send one ray per pixel, you may or may not get a good representation of what is seen through that pixel. So what they do is send multiple rays, and so that goes from ray tracing to path tracing. So again, you can see in the upper left, looks very grainy. If you run it multiple rays per pixel, which takes more time, obviously, you get a much better result. Those results can be averaged down per pixel. So again, this is what it looks like in a scientific visualization. On the left, just hidden surface removal with ray tracing. Then we add shadows in without anti-aliasing, and then we do path tracing to get smoother results. Okay. And the last thing is that often we're not interested in realistic rendering. We want to bring in some artistic, going back to the field of scientific illustration, we want to do things, what they sometimes call toon shading, very popular in molecular visualization now because you can see common structures there, like in the upper right. And here's some work from Bruce Gooch where it shows, this is what we would have with Phong shading. You could see what we might have with ray tracing there in the second one. But by bringing the edges in and some non-realistic colors, we might actually have better communication. Let me come back to perception color maps. I do want to take a 5-minute break. I want to make sure you all will have some chance to explore a few things. So we'll come back to that one. That's kind of the nice way of, or one of the nice parts of breaking this up into different chunks. So now we know that we can do different representations with OpenGL with ray tracing. The Osprey ray tracer from NVIDIA, or sorry, not from NVIDIA, from Intel, because it only requires a CPU, not a GPU, is what's built in. The optics ray tracer from NVIDIA, if your laptop happens to have an NVIDIA GPU in it, then you can actually, you'll see two different ray tracers. You'll see Osprey and you'll see optics that you can choose from. But those are all great for making representations. But we, again, going back to Anscombe's quartet, we want to pair those visual representations with some analyses. So what are some of those analyses we can do? Sure, we can do this before the break. So here's how ParaView sort of lays these out, is you can interact with things by isolating data, you can resample it, you can transform it, you can visually select, you can query and find it. So what might that look like? Well, anytime you are slicing or clipping the data, you are isolating a subset of the data based on its location in the data set. When you do things like an ISO contour or something called thresholding, which preserves the individual cells, you are extracting data by value. Okay, so these are all types of analyses. It doesn't seem like it, but you are doing analysis. You can resample data. So this is one of the things that we can do. That's our friend, the hurricane, or at least the lower corner that is clearly not regular. We can see if we resample that to an image grid, it will actually render much faster. Got to be careful because we are changing some of the underlying data. It's usually better to resample to a larger grid so we're not losing any of the points there. But again, that is a bit of a science in and of itself. But we do have the ability to resample data. That's why we get hundreds and hundreds of filters in ParaView for all the different things that people might want to do. Again, there's ways that you can resample data. If your data is vector data, you can do streamlines. Instead of just a line or a sphere, you can have, like here's a plane. This is the default blunt fin data set that comes with ParaView. Again, we can, in the lower right here, we're showing releasing streamlines from a grid like we might do in a wind tunnel. We can transform data. Sometimes we have digital elevation models and we actually want to, that comes in as an image and we want to extract that up. We can do that. And finally, we can actually go through and individually query the data. So there's a whole range of little buttons on the interface that let us interact with the data. So again, we can probe. We can do the probe filter. We can press through, and let me, we'll end by looking at that, but we can visually select the data. In fact, let me just jump over there and just show you what some of this looks like. Our head. And again, if we put a probe filter here, probe location, then I should be able to sorry, it's not Control P. There we go. I'm not making that great point, am I? The other thing that is interesting, what this shows is what we call the spreadsheet view. Because one of the other things that's nice about ParaView is it lets you see all the data that goes into that representation on the left. So basically it's showing you the structured coordinates and those scalar values from 0 to 495 there. Now again, a lot of those will be very low because that's in the area outside the head, but as you scroll, you can see you can get to others. And so again, we can use that ability to query We can find data. I believe it's just as simple as V. Yeah, and so we can set different criteria for searching for data. And finally, the thing that we can do is we can plot data. So again, we can do a couple of things. There's ParaView allows us to take and create a histogram of particular values. I realize I haven't shown you this one. We'll do that next, but this is part of our nuclear pasta simulation. So we can look at a histogram for any given time step, or we can ask it to plot data over time. Here's a couple from the Cornell virtual workshop going to our head example. And again, with this slice, we can put a histogram there. And so this gives us a sense for the range of values. So we have most of the dark blue, which is basically 0, air. And then you can see the distribution of more dense values in the histogram. And you can plot over a line as well. So you can take and you can draw a line. So again, here you can see as we go from air to skin to bone and then through brain and then back out again, you get that sort of symmetrical view along that line there. So again, it's more than just making a pretty picture. It's trying to do science. It's trying to extract information. So ParaView does give you those tools. Let me jump back and show one more data example. By the way, in the interest of time, we won't do the sources, but note that on the interface, there is something called sources. This actually allows you to add geometry, to create geometry on the fly rather than reading a data set. And so you can see there's not quite as long a list of sources, but things like cones, cylinders, boxes, text for doing annotations, arrows for doing call-outs and stuff are quite handy. So that's what we have in that example. But a real simulation here was one we worked on with a physics professor at Indiana University. I know a number of places have since done this. Some of them might be some of Chuck Horowitz's students who have gone on to other places and continue to study nuclear pasta. So these are the, comes from simulation of neutron-dense material in the crust of neutron stars. And what it does is over time as that as that material expands, it takes on different pasta-like shapes. And then it doesn't hurt that we come in with a color map that kind of looks like pasta, semolina color, and looks great. So we have Swiss cheese or lasagna noodles or spaghetti noodles or gnocchi. And good thing we're coming out of dinner already. Again, one of the interesting things about this is, I think in the download, we gave you roughly 25 data sets or time steps out of what was thousands that they actually recorded. Just to give you a sense of what that looks like, one of the things that's interesting about the simulation is that it expands over time. The actual computational grid is still 0 to 80 in each dimension, but the spatial bounds grows as the energy changes there. So this also shows that in the information you can see that there are 25 time steps in this subsampling. You can also see that the charge changes over time as part of that simulation there. And to get a sense for what that looks like, show you what happens when you actually go to grab one of these. So here's the subset. Notice that ParaView is, again, kind of looking for multiple files that are named the same, except for the number here. So in fact, even in the file browser, it shows them as collapsed. So if you only wanted to grab one of these, you can do that. But in general, people want to grab all of these and read it in as a sequence there. And as always, we go to the Information tab. We see it's a uniform rectilinear grid. And if we scroll down, we can see that there are 25 time steps here. For an interesting representation, we'll go to volume rendering. By the way, we can change these color maps there. We can start with that. And then this brings in the timeline thing here. And so we can see this thing grows. Notice that it won't automatically grow or move the camera back. Needed it. But we can use those buttons across the top to do that. So anyhow, then based on that, we can do animated data. We can actually plot that over time. So again, we can get some more information about what is going on across the various time steps of that simulation. When we want to take a 5-minute break, let people try some things, use the restroom and stuff. When we come back, we'll show you some ways that we can do animations with these. Show you how you can actually export some of these things, share them with people. At the end, my trusty VR headset. One of the cool things about some of the tools we use is that you get the VR for free. You know, if people had to spend a lot of time putting the information, putting the data sets into VR, I'd say it's not worth it. But if you can get it as a natural part of your sharing process, which again I think is very important for emerging researchers in the area to be able to communicate your science and the impact of your work. You know, it's not going to, it can make a difference. You know, I don't think it's going to save bad work it's not going to make bad work good, but it can make good work more visible. So it can help with things like funding, outreach types of activities there. So I wanted to take some time to show you that. And then we'll talk about how we actually go about scaling out Viz. So let's take a 5-minute break. If people have questions, I'll circulate around, and we'll start up again right at like 3:15 or so. Okay, welcome back, folks. Just a couple of quick things about animation. So one of the things that people often want to do when they come to a conference is they want to make a nice movie, put it up on YouTube. Of course, ParaView will do that. Technically, we can animate at least 3 things. We can animate the camera, have a camera move around a data set or through a data set. We can also, obviously, we can animate time. If we had something like nuclear pasta or the brick falling on the can, we can turn that into a movie. And then finally, not always obvious, is we can actually animate parameters of our visualization. So in the interest of time, let me not show you that. They're in the slides there, but this is our friend, the head. Isosurface, I apologize, the quality when I uploaded these to SharePoint isn't good, but I can actually create an isosurface that goes from that minimum value to that maximum value. So again, and you can get a little more sophisticated than what I've done here. Or you can do things like, here was this is of course what it looks like if we were to just say, rotate the data set, again, moving the camera. But we could also change the offset of a slicing plane, get a little fancier here, and we can bounce back up. ParaView is not the greatest. I think I was talking to Andrew about this. There are other tools People often go to Blender or something when they have more complicated visualizations that they want to create. But it's often something nice about keeping that within ParaView. So that's part 7 there in a nutshell. Part 8 is something fun that we've been doing for the last 5-6 years. Definitely we were doing it before COVID, and COVID came along, and it turns out that we doubled down on this, which is ways to go beyond movies and images to be able to share our scientific output. And as I mentioned before the break, this can be a great way to participate in outreach things, get some attention to your scientific work. Of course, there are, I haven't mentioned it, but you can save state. You take some time to put together a pipeline. It's got a number of complicated things. Saving state, just like in any other package, saves that workflow so you can bring it up later. You can also save data. I was just talking to Ali. Again, if we can bring data into ParaView, make some manipulations, we can save it back out. It is possible with those VTK file formats and such. You can write those with your own Python code or whatever you're good at programming, but it's often a lot of work, and if you get one thing messed up, it can sort of mess up the whole thing. So bringing the data into ParaView and just using ParaView as the thing that will manipulate your data and then write it back out in other formats that didn't glossed over it in the nuclear pasta. That was a bunch of particle simulations. They were people called it, oh, look, that's just buzzy dots. These were the neutrons as they were moving around. So we took those neutrons, we splatted them due to Gaussian splat into a grid and turned it into a volume. And that's what you actually have is the volume. So you have a derivative of the original data set that is easier to work with and makes for a nicer visualization. But you have that ability to save data. Of course, you obviously we've seen that we can save movies. We can save different image formats. I don't know if all of you know this, but if you are dealing with images, PNGs, transparent backgrounds, are great, and you can do some editing elsewhere. If you wanted to take our COVID molecule here and change up the way it looks. If you have the opportunity to display your work in a full dome planetarium or a VR headset, you can actually, ParaView has a plugin that will render out things either as 180 cylindrical panoramas or as 360-degree panoramas. You have to use a plugin, but you just Google that and you can get, this was something we did 10 years ago, looking at a galaxy simulation, doing an outreach thing for kids, showing what it'd be like living inside of a globular cluster. The thing I think is most interesting is that ability to output our visualizations as models, because what we can do there is then, and by the way, if you have your videos, ParaView can output, I already mentioned, panoramas, 360s, obviously regular videos, stereoscopic things. YouTube has support for all of that. Again, sometimes you would need, if you're looking at a 360 video on your phone, it'll engage the gyroscope so you can kind of move around and look at it. If it's a stereoscopic movie, you have to have some type of stereoscopic display, otherwise you get that red-green anaglyph. But if you have things like this, like a VR headset, the tools are already out there for sharing this. Okay. One of the cool things, how many people know about Sketchfab? It's about ready to be deprecated. Nobody? Okay, so we think this is actually one of those things that represents the future of what people want to do or should be doing with scientific visualization. Up. So we've got several hundred models. This is a sub-collection of 19 scientific visualization models. So nothing wrong with a good video or a good image, love those, but why not engage users more, actually invite people to be part of the process? We see this a lot now with good journalistic institutions like the New York Times. You know, again, they have these data visualizations that invite you to learn about the topic and to interact with the data. So again, this is all possible now, so we can take this as a simulation, or not a simulation, this is actual lightning strike from scientists in the Netherlands. They have a LOFAR radio telescope. Again, we can put some information here so we can educate people on these. So these are the two researchers that did it. But now we can actually play this animation back in 3 dimensions. You can actually just load this up, the little VR thing. This works great in a Quest 3 or Quest 2 headset. So that's that. One of the things that's interesting, or is actually a limitation of this, is that we can either do animations or we can do annotations. Okay? We'd love to be able to do both, but currently the tool doesn't support that. So here you can see it's static, but then we can actually put some locations and some information in here. Okay? So it's going beyond making it gee whiz and trying to make it educational. And we'll, at some point in the future, we'll be able to do both, hopefully annotations and animations. Okay? So there's a bunch of stuff that we can do with Sketchfab. We'll leave these for you to explore. Our friend Nuclear Pasta, we could either do, we wanted to show the different phases that would go through, so we had to get a little creative and just lay out the 6 of the major phases there with the numbered annotations. Or on the right, you can load that one up and it will play through, but there's no opportunity to educate more beyond the metadata. We've also done something at IU, because we have a lot of display walls, and how do we put stuff on it? And often these things are 8K or more resolution, so and it's not really possible to make things at that resolution and get good playback. So we actually made this little piece of software that lets people put, we're riffing on the term connectome. So this is what we call a collectome, a collection of information. So we can, again, play back. This is all from NASA. We can pull some of the individual scenes out. We can pull the information. There's their, sorry, this is clipped a little bit off the bottom there. But this is an example of what we can do to bring together multiple pieces of more standard resolution types of media in a 4K or 8K display.